Start off with Airborne Ultrasound. So on the left side, you're going to see a representation of the technology and a good seal. So on the left side of that good seal, you're going to have a transmitter, and on the right side, you'll have a receiver. Now, through that middle section of being the seal, Airborne Ultrasound operates by propagating sound waves through the materials themselves. And on the right side, you're going to see a gap in that seal area. Now, when you propagate through a material, you have an airspace and then another piece of substrate, you have a drop in signal. Now, it's very similar to a window, a single pane window versus a double pane window. Now, with a single pane window, sound transmits very well. It's very easy to hear through that medium. Now, with a double pane window, it reduces sound very well. Now, when we have a breach in sterility or a gap between our two substrates, meaning our seal, that's when we're going to see a reduction in our signal, in our sound. And we're going to be able to measure that sound reduction. Now, contrary to that, when you have a cut, a puncture, or an overseal condition, you'll have an increase in sound penetration or propagation. And then your quantitative data will show you an increase. Now, at the bottom of the screen, you'll see some 2D optoacoustic images that present, in this case, a medical paper seal to poly, and you'll see a variety of different different defect profiles. The first being the good seal, and then a side seal inclusion, a channel defect, and then you're going to see a pinhole all the way at the bottom. So all of these different defect profiles are all tested with Airborne Ultrasound, but they all show up differently, which you'll see in some later slides.